In the second lecture, we will talk about plane curvilinear motion initially. Before, we have talked about the rectilinear motion. Now, instead of a straight line, our particle moves on a curve, but still we are on the plane. So there's our curve, this yellow dashed line is the curve, and then you see the arrows here showing us the directions of this motion. And it appears to be at point A at some time t, and after delta t amount of time has elapsed, it moved from A to A prime. Now the amount of distance it has covered is delta s during this time. Okay, during the delta t time, this particle has covered delta s amount of distance. Now, an observer at an inertial frame, so this is our inertial frame, and the observer is at point O. It could be in another frame as well. This could be another frame of observation as well. But let's say this is our frame of observation. Now, this observer will observe the position of A at time t with this r vector. And then, after delta t amount of time has passed, after t seconds, then this particle will appear at A prime, and the observer will observe the position vector with respect to itself, the position of a particle at A prime as r plus delta r vector. So we define this delta r vector, and you guys should remember the vector calculus, right? These are the addition of two vectors adding up to a single vector of r plus delta r. Now, if this delta r can be calculated, so we have this measurement device at point O as the observer, and it observes this r vectors, the vectors to A and A prime as r plus delta r. Now, the difference between them is delta r. Okay? And the time elapsed during this motion is delta t. So if we divide this, now the type of velocity that we are going to get would be an average velocity during this motion. Okay? So this will be some v average. However, if we can make this delta t infinitesimally small, infinitely small, that means if you can make this delta t infinitely small, then this will be written out as dr over dt, and this will be the instantaneous velocity, maybe I can just say instantaneous velocity of the particle at time t. And in fact, as we have this delta t very small, then delta s will approach, or delta r will approach to delta s. So they will be almost equal to each other. Delta s and delta r. Okay, let's move on a little bit. Sorry about that. So we get this average velocity, and as we have already talked about, well, this is a vector now. And the type of derivations that we are doing are vector derivations. So this is delta r vector. We have this as written in bold letters. It's easy to understand this in bold letters when it is on a book. However, as we are writing it on this paper and then on this board, I would like to use the arrow sign for defining the vectors. So I would like to remind you once again. So this is a vector derivation, and as a result of that we get the average velocity vector. If you take the magnitude of it, okay, if you find the magnitude of it, then you get an average speed. This is your speed, and what's inside the magnitude is the velocity. So we would like to call the velocity as the velocity vector, and speed is a scalar, which is going to be the magnitude of this velocity, and we are talking about the average velocity, so we get the average speed during delta t of amount of time. Our average speed in delta t amount of time will be calculated by this magnitude operation. And if it is happening that the velocity is instantaneous velocity, then that velocity will be equal to s dot. S is our path parameter. Is s. Okay, so s dot in that case would be the speed of the particle. And if delta t is infinitesimally small, then we get this derivation as dr over dt, and then we get the instantaneous velocity at time t. And as we make this delta t equal to 0, see what happens now. Let me just try to show that. Maybe I can draw another curve here. I'll show it on that curve. Let me change the color. Okay, so here is our first point, here is the second point. Now I can draw a line like that. So it doesn't look like it is tangent to the curve, but as I bring this second dot closer, then it looks as if it's going to be on the tangent of this curve. Okay. So it becomes closer, 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 and at the end you approach to the tangent. And as a result of that, we can state that the instantaneous velocity is always tangent to the path. And from now on, we're not going to really talk about instantaneous velocity. If we just say velocity, that means the instantaneous velocity, and it will be always tangent to the path. And as delta t is infinitesimally small, then the magnitude of this vector derivation will be equal to the derivation with respect to the path frame parameter or path parameter. So delta, like I said, delta r, oops, this is not a good color. Delta r will become equal to delta s if delta t goes to 0. Okay, so however, this is the magnitude of the velocity. Now, you can also do such a thing as take the magnitude of the vector and then derive it with respect to time. Then that will be the derivation of the magnitude of the r vector, which is not the same as the instantaneous velocity that you would calculate by using dr over dt and taking the magnitude of it, and then this means the speed. This is the speed information. However, this is not equal to the speed. This is just how the r vector's magnitude changes. So it doesn't capture the notion of how the direction of r changes. It's just about the magnitude. So that's the difference. Okay, we use the first one. This is the one that we use for finding the magnitude of velocity of a particle, and magnitude of velocity of a particle is basically the speed of the particle. Okay, let's try to move down. Now let's talk about the change of velocity. We can still argue about that by using the same path. This is our path with yellow dashed lines, and this is the direction with the shown with the arrow. And as you can see, this path is in an xy plane. Okay, this is a planar path. This is xy plane, and then we define this path with respect to xy. That means it doesn't have any information about time. We don't have that information here. However, as we have the information about the velocity at each point, then we know that the velocity now is always tangent to the path. So at point A, it is tangent to the path. At point A prime, it is still tangent to the path. If it was a rectilinear case, then the velocity will be always in the same direction. But as this is a curvilinear case, the direction of the velocity changes. And as a result of that, the acceleration is not going to be in the same direction of the velocity as it is in the rectilinear case. So if this is the velocity for the rectilinear case, then the acceleration will be always in the same direction, or if it is decreasing, then it will be in the opposite direction, but in the same line. Okay. However, in a curvilinear path, because we are taking a curve, that means the velocity vector's direction is changing. There is a component of the acceleration that is used for the change of the direction, and another component of the acceleration that is used for the change of the magnitude of the velocity. And as a result of that, the acceleration will never be aligned in the velocity vector's direction at any time if the motion is not a rectilinear motion. If it is a curvilinear motion, the acceleration, the instantaneous acceleration that you would calculate will be always in a different direction than the velocity vector, and the different direction is decided by the curve. So as this curve looks like that, the instantaneous center of curvature is towards this direction, and as a result of that, one part of the acceleration is towards that direction. And the other part of the acceleration is towards the velocity. So this is the velocity vector, and some part of the acceleration is along the direction of the velocity, and the other part is along the instantaneous center of rotation. And there we have a perpendicularity. It will be always perpendicular. Think about the circle. Draw a tangent to the circle. From the center to that tangent, you will always have 90 degrees. Okay, wherever you are. Here, again, the same 90 degrees. Anyway, so from point A to point A prime, the change in the velocity vector is defined as delta V. Again, we have an elapsed time of delta t. If we divide this change of the velocity vector by delta t, we get this average acceleration. It's a vector again, because we are now dealing with curvilinear case. For the rectilinear case, you don't have to define it as vectors, but for the curvilinear case, we would have to define it as vectors, because it's going to have two components in plane. In three-dimensional space, it's going to have three components. Anyways, so as we take this delta t to 0, so infinitesimally small time has elapsed, in that case we find out the instantaneous acceleration at t, calculated at time t. Now after this point on, now what we have defined is delta r, taking delta t to 0, and then doing the derivations, we have defined the velocity vector and the acceleration vector. Okay. Now, these vectors are delta r, v, and a are free from any frame, but if you like to define them, you need to choose a frame. Okay, you can choose your frame here at point O, or you can choose a frame here. Let's say this is x prime, and this is y prime, and this is O prime. And then define everything with respect to this frame. So you draw these r vectors. Okay, this is your r vector, this is r plus delta r vector. And then define this motion with respect to this frame, if you like. but you have to be consistent after you choose your frame. Okay, if we have chosen this frame, X, Y, and origin at O, then we would have to do all the calculations with respect to this frame. But then the type of the frame can change. We can choose to use rectangular coordinates or path coordinates or polar coordinates, and that will be dependent on our nature of the problem. Whichever one would be easier for us to solve the problem, whichever one will be more intuitive to solve our problem, we're going to choose one of them. So the options are rectangular, path coordinates, which are the normal and tangential, or NT coordinates. Remember, we should say it NT, and polar coordinates. And among these, like I said, you can choose any of that with respect to your needs in your problem.